and I welcome our speaker, respected Professor Ludger Obeck. Sir,
yes, good
participants
morning,
are slowly
everybody.
joining. Yeah, so now you can start.
Okay, I share now. There's something different here. So, okay, that's sharing doesn't work. Did not work. Share, okay. Okay, good morning, everybody. You had already a lecture. So that's your first lecture of today, and it was planned that we will go to continuous time finance or continuous time models. But first, yesterday, our last topic was concerned with American options, which in stochastic analysis are related to optimal stopping.
Yeah.
So this means the payout. I don't know whether in the other classes you already had mentioned American options. The American options you can execute every time, and then you get the payout, the contractional payout. So the let's say stopping problem is to find an optimal stopping time, such that the gain, this is a payout of a put option if you stop at time tau, and x is the value of the underlying asset. And we will see this is handled by what's called the Snell envelope. Okay. So if you have an adapted integrable process, and so x is here actually denotes, if you think in terms of the option pricing, that's the payout at time n. So what do you do in option pricing? Each time you think, okay, what do you want to do? You want to execute. So if you execute, then you get this one, and this is if you not execute. Now we will later see this in the application. So currently we just define it like this, non-execution at time n. This means the value of the option if you don't execute is set n. But mathematically that's called what's called the Snell envelope. You can also, what we are now doing is to find a maximum of a payout function. If we don't have a stochastic problem, the American option, we have just one path. Let me find a place where I can draw a picture. So let's say we have only one path. That's time. That's your payout function. At time 0, you will get this one. Now you have a function. If you at time 1, you get this would be your payout. And so on. And let's say like this. We have a function like this. Let's put it like this. That's your payout in a given path, huh? At time t. Huh? So how do you, what you want to do? You want at this path, we don't know yet, but let's assume we have it, path of a payout. You want to figure out this point. This point would be a maximal payout. A very complicated way to find it, and that's what we will do actually. We take all, and you want to find this stopping time. This is your tau. Huh? In this case, it's obviously like 3, yeah? But you want to figure this out, and without knowing it. Yeah? So to describe this one, what we do, we take all, let's say, functions, make them like this. You take all functions which are above this one and which are increasing, and which are decreasing. So this function, the blue function, that's a function, we call it yn, which is larger than the blue function, your xn. And which is decreasing. That's a decreasing function dominating xn. And then, of course, you take the smallest one of this. Smallest. You take the smallest dominating function, which is obviously this one, which we call epsilon n star. That's the smallest one. And tau is the time when smallest dominating decreasing function meets xn. So that's a complicated way, a feasible way to figure out this optimal stopping time. One. Of course, you might have a second one when it's here, but at least this gives you one stopping time where you figure out the maximum of the blue part. And that's called the Snell, and you will see this will be done by the Snell envelope. Okay. This is a Zn. So keep it. Zn is the maximum of xn of your p out and the expectation of Zn plus. So it defined backward. Zn equals xn, and Zn is the maximum of xn. This is what you want to cover. You want to dominate. Or the expectation of Zn plus 1 given Fn. You start with an xn, which is a p out, if you exit at time n, and Zn is a Snell envelope. It's the largest, the smallest dominating supermartingale. The supermartingale are decreasing in average. And you see this is defined backward in time, which happens quite often in mathematical finance. So then the theorem tells you that Z is a supermartingale. This means on average you have the expectation, the future expectation which we in a deterministic case where we just have one path, it's just decreasing supermartingale means on average is decreasing. Yeah, so the Snell envelope is the smallest dominating supermartingale. And I try to explain why we do this, because we want to figure out the stopping time where we reach the maximum of the path, the payout. No? Of course, by the definition, it's obeys a supermartingale inequality by definition, because set n is larger than this one. No? If you want to find a supermartingale like this, you just define it like this. Yeah, but we still have to prove that's the minimal one. No? So that's done in the proof. We take another one with these properties, and then we will show that this is also smaller than yn. This is this little proof here. Okay. And so this tall star, that as I have done it in the picture, so on a single path, this is our tall star, which we will see later. That's the first time. And then the blue one, not the blue one, the violet one, this one, if we stop it at this point, it just becomes straight. So this line is the yn stopped at tau star. So it remains on the value of tau star. And that's in a martingale. In a deterministic world, martingales are constant functions. In probability, it's just constant in, it's just constant in expectation. So even it's, of course, in deterministic world, it's a very complicated way to find this time. The index where the function, it's a arc min of the max in analysis. But so in stochastic analysis, it will be the Snell envelope. And so this tau star, this we want to find. If we do want to find our optimal execution time in mathematical finance, the Snell envelope. The Snell envelope is a minimal dominating supermartingale of your payout function. There's no assumption on x, and the payout might be prices are martingales, but payout can be anything. That's like your payout in function, payout in European option can be any measurable function. So payout in an American option is just a sequence, also a stochastic process. In this case, it's xi. The contract writes, in the contract it's written at time 3. If you execute at time 3, you get x3. And so you can execute, and for each time point you can execute to get a certain amount. But so this tool of a Snell envelope tells you exactly when to execute optimal. So this means, of course, that's the price. The price is then the expectation of x tau star under the risk neutral, under the martingale measure Q. And so you see already here in this definition, that's what you do in option pricing. You compare at each, you go backward. This actually you do in a binomial tree. In binomial tree to figure out the value price. American option. So at each omega in time, this means at each node, American option. Yeah, in the tutorial we might do it more explicitly.
Excuse me, sir. Sorry for the interruption. Sir,
Yes,
but I have
please.
one question. Sir, how
Yes, please.
does the Snell envelope behave under different filtration? Sir, how does this Snell
Yeah.
envelope behave under different filtration?
You mean if you define it, so I mean it's the xn is adapted to a fn.
Yes, sir.
So
Sir,
if f,
yes, sir.
so you mean if xn is adapted to a different filtration, it's defined for each, for another filtration you will have of course other values, because this will be different. Now, of course, this value depends on the fn.
Okay, sir.
In this sense, it's defined for, you start with a stochastic process, xn, which is adapted to a filtration fn. And for this, you define, because these will be different for different filtrations fn. Of course, you are correct. Xn might be adapted to different filtrations.
Okay, sir. Sir, but in that case, the optimal stopping time will also be different for
Yes.
different filtration.
Yes, in this general setting, but of course in financial markets, you have just because your xn is actually a function of usually of the underlying asset, so it's adapted to the to, I mean, this is, I mean, I don't know whether your question is concerned with American option pricing or more theoretically. Yeah, theoretically, it depends on Fn. Finished. Yeah, in mathematical finance, Fn is the filtration generated by the price process. Yeah? And the payout Xn is also adapted to Fn. So there's one fixed filtration in mathematical finance for pricing. And financial market is always defined for one filtration. I mean, what we do here in kind of risk neutral pricing, we just have one filtration Fn.
Okay, sir.
Of course, in theory, you are correct. There might be different, there are different values of Zn. Zn is then already different, Zn, and so Tor will be also different.
Sir, but then how can we choose correct filtration? Because for different filtration, the value will be different. So in that case, the payout function will also be different, I guess. So how will we
yes, but as I said, in
choose the
mathematical
correct one?
finance, yes, but for pricing, you just have one filtration. Because the market is, Fn is a filtration which defines the market.
Yes, sir. But my question is that how do we know that this filtration works well for this financial market?
I mean, it's generated by the price process. Huh? So we haven't not yet defined a financial market in terms of in discrete time. Huh?
Okay, sir.
Yeah, I will define it shortly. Yeah?
Okay, thank you, sir.
Yeah, yeah. So that's, we are now preparing. We are in the preparation of defining a financial market. Huh? Okay, this was just basically did not want to talk, that do not want to talk so much about American options. But yesterday when I mentioned this, it was asked that I do some more details today. Huh? Okay, so as I said, we might do it in a tutorial. Huh? Okay, after some, the last topics were kind of basics on martingales, like definitions. I didn't mention, and the only thing I mentioned it that if you have a martingale transform, you can get a martingale if you start with a martingale. This means in mathematics, we come later to this, if under the martingale measure, which it's a measure Q, which makes the price process discounted to be a martingale, all all portfolio strategies will also give you a martingale. There's one property I mentioned about martingale. The second one, if you stop a martingale, also your expectation at the stopping time will be the same as the start. Also, in this sense, also the martingale property remains that stable. The expectations are constant. Also holds for stoppings, for stopping times. No? This means there's no stopping strategy which gives you on average a gain. Okay, as the financial market in one period consists of a vector of d plus 1 assets. Here we have a vector of d plus 1 assets at every time t. And so you see we start with a filtration. So that's fixed. That's a market filtration. And usually, and let's say put it like this, in applications, you start with a process and then define f to be the filtration generated by the process. But I mean, that's up to the practitioner. But the economist always tells you market are efficient. All information is in the market. That's a question of, let's say, non-quantitative financial markets assumption. Okay. So we start with the process. Now these are multiple assets as well, and and we have one positive process. Okay. This is not necessarily in the market. Sometimes it's a market, so that's why we so we put the numeraire. So the numeraire is just how we measure everything. It might be dollar, it might be a currency, it might be a discounted currency, and so on. But numeraire is something, the only thing we need for it has always value, it's always positive. Again, this means there's no default in this market. So there's one asset which does not default, which is never the value 0. That's our numeraire in the sense as we measure the prices. In our case, it will mainly be be the first asset as 0, the first stochastic process. And then in this case, we have a trading strategy. But again, you see the only important thing about the trading strategy that you have to decide before how much you want to invest. At time t minus 1, and then you have to wait one period in order to know how this investment will evolve. That's, as I call it, that's predictable. This is thought as a number of investments in asset I at time t. And phi it can also be negative, that's short sellings, and can take arbitrary numbers as values. And then the value of a trading strategy, that's a scalar product. And so it's always before you do your new, let's say in real world time points, the value at day 3 depends on your portfolio decision at day 2 and how this evolved until you do your new investment decisions on day 3. So VT, because phi t is ft minus 1 measurable. These are decided at the before, so at that time, the value at time 3. You think about this is the value before you do your new investments. Yeah. And so the change in value of your portfolio, if when phi t, because at more or less at time t minus 1, you bought your portfolio with amounts phi t in asset phi it in asset sit. So your profit and loss from day 2 to day 3, you decided on day. On day 2, you decided this was your cost. This was a portfolio right after the decision, the amount as the value when you bought it, if you like, and this is somehow when you sell it. But buying and selling is just reevaluation. And so that's then the gain process. It's what you gain from your trading strategies by all times between time t and starting time and your profit and loss accumulated. And here you see that's your martingale transform. Which we had before. A martingale is so important. If this one is a martingale, then also your portfolio will be a martingale. Okay. So that's now we come to the numeraire. So you can before our numeraire somehow, if you like, was 1. 1 was 1 was 1, which is in reality is not the case because €1 has less value in 1 year time, or more value in 1 year time. Or it's better to get now a euro than to get a euro in 1 year time. So on. That's if you like, discounting or numeraire, or whatever you want to call it. That's kind of. It just makes the mathematics more complex, but basically it's you can take the numerator to be 1, so s tilde equals s, but we have to discount if you want to be more realistic. That's a discounting factor. But if you discount, also you have to discount your gains, and then you have the martingale transform with the discounted process. So the next topic is the next definition is more important. That's the self-financing, and that's natural. That's the thinking. Okay, you do one investment at time 1. Or t equals 1 means at time 0 you have decided an investment. And then you take money. And this money you invest in, you divide it according to your trading strategy, phi 1. But then in the next step, you just can reshuffle the value. This means if if tomorrow, your portfolio has a value of 1 million, you can just take this 1 million, so it means selling this portfolio at 1 million and buy a new portfolio with value 1 million. That's a self-financing condition. This one is your new portfolio decision allocation, but the total amount you allocate is the value of your portfolio before you reshuffle, before you reallocate. That's what's called self-financing. In this case, the value process, nothing else as a gain process plus the initial investment. But that's clear. So you have an initial investment. This you have to get somewhere from. And then in the other period, you just reshuffle. And that's a self-financing condition. And then you see, if you see the indices, so with a fixed T, you have the delta, the increase of the your gain. Then your value process equals the gain process. And so this means self-financing for S or S tilde doesn't matter. So discounting, for the discounting process, it's also self-financing if it's self-financing for the non-discounted process. So this means, from the definition point of view, if phi is self-financing with respect to S, it's also self-financing if you divide anything by a, if you divide S by a positive process. And so that's the most important property here from self-financing. So phi, capital phi is now the set of self-financing strategies. And so it's very, from economic point of view, it's very natural condition if you do a trading strategy. This means when you trade and when you have your portfolio, you can't go to somebody else. Can you give me some money? I want to invest some additional money. Each time you reshuffle your portfolio, you can also only take the money you get from your portfolio, from your old portfolio. Put it like this. And then this is important property. Then the value, that's the value, is obtained from the profit loss of your process, which is called the gain process. And here you have this mathematical object, then the martingale transform. Here you see in the proof somewhere appears a self-financing condition.
Excuse me, sir. Sir,
Yeah.
I have one more question. Sir, is it possible
Yes,
to have a arbitrage opportunity in self-financing portfolio?
Yes, if the market is not arbitrage free, you find a self-financing. Before in our one period model, we don't have this property because we didn't reshuffle. We just period. So arbitrage possibility, arbitrage portfolio is defined to be a self-financing portfolio which gives you an arbitrage. Before we didn't consider self-financing because we only have one period in time, one time period. Now we have to do the self-financing in order, because as I said, that's reasonable. Of course, lending money is allowed, but you have to give it back. So let's say from a financial point of view, that's not a big issue. If you can say, okay, you can always lend money, but you have to give it back. Non-self-financing is only if you get a gift from somebody, some money, you ask your grandfather, okay, don't you have 1 million for me to invest? And then he doesn't care whether you get it back or not. But as long as lending money is allowed. But you are correct, arbitrage possibilities are those self-financing strategies, which gives you an arbitrage in the definition that you make out of something which is zero at the beginning, you make something which might be positive with positive probability. Yeah? But this will come in the definition. Yeah?
Okay.
Okay. Yeah? And so I don't know whether some of you have already some experience with stochastic integrals. Later, self-financing gives you that the value is a stochastic integral. Yeah. Yeah. So this is discrete. So far, it's a discrete time integral. But this later becomes, and it's a very specific one. That's why I emphasize this all the time, that this one you have to decide. So t plus 1, this one you have to decide at time t. Of course, in continuous time, there is no t minus 1. So the concept becomes a little bit more evolved. Okay. So, but let's say from a mathematical point of view, this self-financing, if you like, is only to convince the people applying this that this is a reasonable way to use stochastic integrals. Because if we don't consider the investment in the riskless asset 0, and as I said, that's like money. So investing in money is like lending and and saving on a savings account. But you have to put it back and forth. If you just invest in risky assets, let's say you can always find a lending strategy in your money market account, where you can have overdraft or whatever in your money market account and your credit line, that you get a self-financing strategy. So each investment strategy in risky assets can be financed from an initial investment and borrowing and investing just money. That's also reasonable from a application point of view. I mean, that's just only to answer the question, why do you use stochastic integrals in mathematical finance? Because you can always relate it to a self-financing strategy. Okay, and that is preposition. And it's also reasonable if you want to invest a huge amount in risky assets. Of course, you can finance it by lending money. Okay. Okay. So now we come to the definition of derivative in this context, but that's every ft measurable random variable, which is integrable. So that's the only condition we do technically. We need an integrable random variable. And then in mathematical finance, that's called a derivative. And it's a derivative because it's ft measurable, and ft is the same filtration where you see your price process. Okay, and then we extend the notion of arbitrage in this context, and you see arbitrage is already defined only for self-financing strategies. Of course, for non-self-financing strategies, put like this, the money you get as a gift from your grandfather, that's of course an arbitrage. You get money and you don't have to pay it back. Yeah? But it's as soon as you just have an initial investment, yeah, and then you exclude arbitrage properties and you have an arbitrage-free market. Yeah? And arbitrage is defined as before. Yeah? Yeah, you see only the first timing point 0, and the final time capital T plays a role. What you do in between, you can be very clever, but your goal is at final time T, yeah, you have a portfolio such that the value of this portfolio is non-negative, always with probability 1, meaning you will never have a real loss, and sometimes you have a real gain. That's the arbitrage we had before, just in now you have time points in between where you can act. Yeah, but as I said, we only look at, for our pricing exercise, which we do in this lecture, we do assume that there's no arbitrage. And in this context, we can prove that more or less the entire market is arbitrage-free if each single period is arbitrage-free. Yeah? Where we have here R, that's PT is a partition sigma PT. Because technically we still have here discrete space. The sets PT generates FT, and we can assume that P of A is larger than 0 in order to have this elementary defined. But if you know some measure theory, of course, that's just that you know this definition is elementary if A has positive probability. So this means a market is arbitrage-free if each of the single period markets has no arbitrage. This means if you want to make money up to time capital T, you somehow have to make money somewhere in between. And if you can't do it somewhere in between, you can't do it up to time capital T. That's natural, but of course, in mathematics, you have to prove something like this. Okay. So basically, in our current mathematical setting, where everything is, you see here, I mean, it's difficult. I think it's difficult to teach it online to go through these proofs in order that you see if you have an arbitrage, then you can construct also an arbitrage for a single period.
Sir, you may just give a glimpse of it, and you may skip the proof if you wish.
Yeah, I skip the proof.
Yeah.
But basically, I think
if you wish, you can give the outline, some glimpse about it.
I give you some outline. So the outline is still too much, so I will condense it again to what I was talking about.
Okay.
But basically, in non-mathematical words, it just means if you can make money from today until 10 days, there must be a day in between where you make the money. Meaning making arbitrage, making riskless money, from 0 to from now up to 10 days, there must be one day where you do this riskless gain. Put it like this. Okay, and then of course technically you can use with the same techniques. You have a martingale. Now the martingale measure is you have to define it properly. So we take now a new probability measure on F omega capital T until final time, which is equivalent with P. This means if n is a p null set or zero set, then and then n is also a p star zero set. So this is absolutely continuous. And then that's the one definition of a martingale measure. Usually it's called equivalent martingale measure. Like in, martingale measure. Then you assume it should have the property that under P star, the discounted process is a P star martingale. This means under P star, we did not. That's our ST divided by S. We have the problem. I think we discounting FT equals STI divided by ST0. The discounted process is a martingale. This means your expected gain on the discounted prices is the same. Or I mean, you can rewrite it and saying, okay, your gain is the same as the riskless rate. Let's see if ST equals S0T equals the interest rate, a simple one. So that's the simplest way to put it economically. You never earn more than the riskless interest rate. Or like the inflation, the value of money, whatever you call it. This is just the discounting. I don't know whether you're familiar with this, but that has nothing to do really with mathematics. It just makes it more adapted to what value means. On average, you don't gain, because everybody will gain by sleeping if you put 100 euro into to the government and you get after 1 year, you get 105, whatever the interest rate is. That's not really gain. And so the first preposition that's important is if you have a martingale measure, P star, then also every portfolio discounted will be a martingale under this measure. So that follows from the theorem I also gave you that martingale transform of martingales are martingales. So now we put this fundamental theorem that arbitrage-free is equivalent to existence of martingale measure. Now we assume this assumption is there is a P star such that S star is P star martingale. S tilde is P star martingale. Then the market M is arbitrage-free. And the proof is really easy. If we have a self-financing strategy, then phi tilde phi is also a martingale under P star. In particular, the expectation is the same. If we have now a strategy which is non-negative at final time and start at 0, that's one necessary assumption of an arbitrage phi. An arbitrage phi must fulfill we start with nothing, no initial cost, and we end up non-negative. But then it follows, because you have a non-negative variable whose expectation is 0. That also a non-negative variable with 0 expectation must be 0 almost surely. It's very simple. Just from the martingale property, you know that there's no arbitrage. Whatever you do in between, you can go negative or whatever, but if you assume that at the end you are non-negative, and because it's a martingale, it has the same value on average as your initial cost, but the assumption on an arbitrage strategy, you start with nothing, you get something non-negative with positive probability, does not happen. It's very simple.
Hello, sir.
Yeah.
Sir, how you can analyze that such martingales are appear in our financial market? Can you give some example where we realize such martingales are exist in really?
Yes. Yeah. So if you start with this up and down as we have done before, this is also like in the tree, in the binomial tree. You say your market is a random walk.
Yeah.
And then you find a P star, such that this random walk is a fair random walk, meaning P star equals 1/2, 1/2. Then everything are martingales. So you are correct. So that's a challenge. If you start, the first challenge, if you start with some, let's say, market model which you might have estimated from somewhere, or your assumptions on the model, like it's a diffusion model, and this we will see later. If you start with a diffusion model, in most cases, you find a P star. Now, let's say, I don't know how you are familiar with, like if you start with Brownian motion with drift. The question you have here, do you find a P star such that your Brownian motion has drift, riskless drift? The increase is, the discounted is a martingale. That's really a very good question, because that makes it, put it like this, this makes mathematical finance not just computing, this makes mathematical finance mathematics, because you have to understand the structure of your market, which is just a filtered probability space. And you have, in order to find properties, structural properties, you have to understand the space of probability measures which are absolutely continuous with respect to your starting measure P. And then you have to figure out, is there one measure in this set such that the process is a martingale?
Sir, but sometimes it is difficult to analyze, but how we can say such things are really appear?
Really, in markets, there's no reality. It's different from physics. I don't know whether, so that's always it. There's no physical.
Oh.
Of course, you can, let's say you start with a statistical model of your market. You say, okay, this S are like diffusion processes.
Yeah.
And in most cases, you find a martingale measure. And then you have, in order to price arbitrage free, you can use, of course, you can say, okay, I think in the market are arbitrage. Then you can skip all of this. So the basic assumption is we have here, there's no arbitrage. And actually the economists buy into this argument, because they say if there is an arbitrage, of course there will be people seeing this arbitrage and trading, into this arbitrage, and after 100 trades, arbitrage is gone. Yeah? So this means the clever application of this, which you, of course, you might learn in some instances, but usually it's more a question you observe markets and you have, because you know how an arbitrage-free market should look like, you should figure out that there might be some prices which contradicts the non-arbitrage hypothesis. And then in these prices, you have to invest. Like I give you the very fast example where there was an option price given, and we saw that's not arbitrage free. This option price is not arbitrage free. I mean, put it like this: all these tools which are provided by arbitrage free pricing should tell you where I find an arbitrage. And you have to be faster than anybody else to make money out of this arbitrage. If you actually want to make money out of this arbitrage, the best way to make money out of this lecture is, of course, to go to the employer and say, okay, I know Black-Scholes formula perfectly.
Yes, sir. Okay.
Sorry. Okay, you see martingales, and that's the main application there. This simple statement, this means if you find this martingale measure, you start with some markets which you might think is useful, describes to some extent the data you see good, and as I said, you can do like diffusion processes, Levy processes, and in all cases you find an equivalent martingale measure. And of course, we will, like in discrete time, it's, and so the inverse is also valid. If M is arbitrage free, then we find a martingale measure. This is more complicated it's kind of an extension of this hyperplane separating theorem, because, as I said, our current running mathematical assumption, omega is finite, so everything is finite, everything can be embedded in Rn. So you take the positive random variables in the sense that there's one omega. As I said, omega is finite. And we have also assumed that p omega is larger than 0 for all omega in omega. Just to make it simple. Then it's just counting omegas, weighted omegas, weight omegas, put weights on omegas. Under these assumptions, everything looks like you have L++, and you have all the set of reachable portfolios. This we called gamma before in the picture, and this was called K, more or less. And then we have the same separation of these two, and we can put a vector on it. So the picture is the same. This was anyway wrong because we had n equals. We can only draw capital N equals 1. Now we have, but still finite dimensional. And the same holds for your gain can also not be positive in one instant. Because for all our arbitrage theory, v tilde 0, we start with 0, so v tilde, the value is actually the same as the gain because we have no initial investment, so that's equivalent for arbitrage. If phi is a candidate for an arbitrage theory. Okay, now you see that the same. Okay. So just to mention how it works in more realistic models, in continuous time, continuous space model, then omega is not finite. You have general omega. You have to restore to Hahn-Banach theorems, separating hyperplanes in finite dimensional space can be related to Hahn-Banach theorems in functional analysis. No, another way to prove it is the one which I try to explain in words. That in this case, we had one period finite state model. And so if we have finitely many time points, we need to have at least, if it is arbitrage, there must be an arbitrage in one of the time points, time intervals. So that's equivalent to this one. So this is the main theorem here. The market is arbitrage-free if and only if there is a measure P star, which is equivalent to P, and such that the discounted asset prices are martingales under S tilde, discounted asset prices S tilde are martingales under P star. Okay. Now we more or less say Ft. Mathematically, this means Ft sigma S, the vector S T equals 0 to T. So the filtration is now generated by Ft. The filtration is generated by S. Now we take a replicating strategy, meaning, can you hear me? Hello?
Yes, sir. You are
Yeah, because I was told I was muted, but it's fine. Okay. Okay, now we take X, which are not, this tells you are just functions of the underlying asset. And this means it's, of course, a specific function because this can be written as we have seen before, as I now write it like this is stochastic integral. So in our context, it's a martingale transform. So our real formula we had here was V phi0 plus some phi t delta st. But let's assume we already have understood that this discrete sum is a specific integral. The specific integral is because the phi is predictable. Phi, before change of S appears. Now, the replicable, attainable claims or derivatives are those which can be written as stochastic integrals. or from a finance guy can be the value of X can be obtained by a hedging portfolio, a replicating portfolio. Of course, if this is replicable, then the risk neutral price is the value, initial value of the trading strategy, which is always the same because F05 is deterministic. Today, everything is deterministic. It doesn't depend on the measure you have chosen. Okay, and then we have, if it's arbitrage free, then you have a unique price of an attainable claim is always the same. That's clear that just by the arbitrage property, if at the final time they are the same, let's say we have even two replicating strategies, phi and psi, but the value is the same because the value should be X. So this means the values of the trading phi and the replicating portfolio phi and the replicating portfolio psi are the same. Also, the initial values are the same. And here it's shown that at any time it must also be the same. So if you have an arbitrage, of course, there must be a first time where they are different. This might be 0, but then you can see that this gives you an arbitrage strategy, which is clear there must be a set of of positive probabilities such that if they are not equal, there must be a set where there are a larger one like this or other way around. And if this happens, then you of course invest in phi. Now you buy psi and you sell phi. You make money out of this. But the strategy at the end, then you wait until the end. In this case, you just do nothing. Riskless asset investment. In this case, you sell and buy, and in this case, you sell and buy and make this money. You put this immediately into your saving account in your safe investment in S0. You make this money at the end. Even you discount or you don't discount, doesn't matter. This gives you an arbitrage. Of course, you have still to say that this strategic size self-financing. So here we see already if M is free of arbitrage and X an attainable contingent claim, this means can be written as a stochastic integral, then the arbitrage price process is given by the value process f phi t of a replicating strategy phi. Even if the strategy might be different, the value of the strategy is the same. As in the one-period model, the price actually, to get this price, is you don't need the replicating strategy. You just take the expectation of the discounted payout. This discounting, we had to assume that it's deterministic. Minus t, it's plus t. Okay, it's just interest rate. Huh? You can also whatever you do, however you have defined it. I think in this context, I still have done this one as discounting. Usually you do, of course, this your discounting. Huh? But it depends on your discounting assumption. But anyway, that's deterministic. Huh? And so then this is a fair price. Huh? It's a unique price. Huh? It's also the same for each martingale measure and so on, because it's a replicating price. Yeah. Yeah. And so you can calculate it like this. Yeah? This means if you have now a model and you have a claim, what people do in practice, even if you don't know whether it's replicable or not, you just take one martingale measure and you calculate this price. The problem is, if it is replicable, that's the only one. If it's not replicable, you're running into problems because there might be different martingale measures. Okay.
Excuse me, sir.
Yeah. Yes, please.
Sir, what would be the possible such cases in which replicating strategy wouldn't be unique?
If you have multiple martingale measures and non-attainable claims, then you have an interval of prices. That's what's called incomplete. Incomplete markets. This leads to price intervals. Theoretically, you get an interval of prices. It's similar in bid-ask spreads and so on. Each deviation from this theory I will present gives you an interval. But the techniques are similar. You work with martingales. You work at least with stochastic integrals. You do the hedging. The hedging. So the replicating, you do super replication. This means you find always a portfolio which is larger than X. So as a banker, you will be safe. And of course, as a hedger, as an investor, you want to have that's the replicating. You have the that's the highest price. Replicating price, and then you have the price of the buyer of the option. And then you have to agree somewhere in between. In real life, then you have to find, but at least you know the boundaries. Okay, because it becomes complicated if you have multiple prices and non-attainable claims. In most simple and most real-world examples, you have a complete market. This means a market is complete if each X is replicable. This means for each X, you find a phi self-financing such that this strategy gives you the output. No, that's very nice. Because if you want to learn mathematical finance properly, actually you have to learn stochastic analysis property, because this tells you all models we have the property that all random variables can be written as stochastic integrals. And we come back to this. What does it mean? It's the deep mathematical result of this is whether P has the martingale representation property. And as I told you, that's why it's called mathematics and not computing. Yeah? The question of your financial markets, the first question, fundamental question of your mathematical models where you want to price is, does P actually the property of P and their filtration and your process S has a martingale representation property? If this is the case, then your market is complete. And then you can do this risk neutral pricing in all circumstances. And that's equivalent that there's only a unique martingale measure. As I told you, P it's a set of martingale measures. It's a subset of the measures which are equivalent to P. It's actually a convex subset. The set of equivalent martingale measures is convex. If you have two, you have many, because each convex combination of two will give you also a martingale measure. So the analysis of the space of martingale measures is somehow in the background of this abstract type of mathematical finance, put like this. Okay, market completeness. The market is free of, we assume you have one martingale measure, and then M is complete, even only if there's a unique equivalent martingale measure. Of course, you can also ask for completeness in this, whether you have, that's what's sometimes called robust finance. That's in pathwise. You don't care about probability measures. You only care about replication. But of some kind of, in a very weird space of functions. And replication means still this pathwise stochastic integrals. These are not like Riemann integrals or Lebesgue integrals. So these integrals are very specific. And so in, let's say, robust mathematical finance, which does not care so much about the P star or P's, you still have to answer this question pathwise. But for functions like this, if you see, that's your S. And how it's usually it has no finite total variation, so you cannot really write this integral like this. Okay, but that's another branch is robust mathematical finance, which is a kind of different branch, which I do not present here. Okay. The proof. We have to show that if you have two martingale measures, then it's the same. But that's clear because probabilities are. We know such that the price is the same, but the price is the expectation of martingale measures discounted claim. That's how it's the same today. Because it's arbitrage free, it must be the same. That we have shown before. If you have attainable, there's only one price in an arbitrage free market. So this means arbitrage free gives you there's only one law of one price. If not, we can construct an arbitrage. And we know from martingale measures, that there is a martingale measure, that we write the price as an expectation, discounting claim, expectation martingale measure must be the same. Okay. But this more or less means, if you put now here indicator function, you have derivatives, you have digital derivatives, you get $1 if A happens. This actually appears. In some markets, we have this all or nothing derivatives. Really bets. You just bet that the Indian stock index is larger than 10,000 next year, then you bet, okay, I will then get 1 rupee or 1 million rupee or whatever. Even, I mean, our abstract sense, of course, we claimed that every X is attainable, replicable, in particular this one. And then you see that the probabilities are the same. Okay, because prices are unique, put it like this, martingale measures are unique. Now we assume that it's incomplete, and we construct 2 martingale measures. And if it's incomplete, this means there is, because it's a vector space, put it like this, there will be one. I mean, that's then like you can say there's one which is not in the set. These are the set of attainable claims. It's a linear subspace, and so in some you can embed it in some Hilbert space. In this case, we take this scalar product. You see, it's like the L2 scalar products if you do it in general probability space. But here for that's L2. Because it's finite, but that's also go through to in L2 spaces. You have an element which is not in your subspace. It's a real subspace. You have an orthogonal element, which we call set. T tilde is a real subset of a real subvector space. This means in this Hilbert space L2, you have an orthogonal element to this space. And so this set can be normalized to be a density. Then this gives you a density, and you can define a new probability measure P star star, which is another martingale measure. Okay, so this means, and we have to prove martingale property, which comes from the orthogonality. Comes from the martingale property of P with 1 star, and the orthogonality of set to this entire space. Attainable claims. These are attainable claims. There will be 0 with a set, and so on. Okay, so these are martingales. Just this remark which I have done before. Attainability of a claim X is equivalent with the martingale representation of the martingale. So this gives you a martingale anyway. BT gives you a martingale. And you want to represent it by the fundamental martingales. But that's more or less to say that each X, if you put a capital T, then you have, because it's FT measurable, this means VTX equals here from 0 to T. That's what I mentioned before, that each random variable can be represented by a martingale with respect to your driving or underlying price process. Yeah, that's a property of omega P, F, and S. Actually, of P star, if you like. Yeah? No, because that's only under P star. Now, if you have a complete market, you have this P star, and the completeness is a question of martingale representation. And as I said, that's a classical topic in stochastic analysis. Other books in stochastic analysis. No? Okay. So that's whether we can write each x as an v0 plus integral phi ds. Now I'll put it like this: each martingale, call this mt, is a function of t as m0 plus integral COT phi s dss. Let's say we have p star equals p and s tilde equal s. Yeah, this reminds you to which theorem you all have learned. Another fundamental theorem. I write it differently. I write it as m of t equals m of 0 plus integral 0 t phi of s d s sub s. Divided x t. Which fundamental theorem looks the same? Any idea? Write it down yourself.
Sir, Picard distance theorem.
Doesn't work. D. So if you don't tell me now, I tell you after the break. Huh? D. Let's take a function, capital
Maybe by
X.
that time they will also get to know, sir. They will search here and there and they'll find it.
It reminds you, you shouldn't look, you should look in your mind. Don't look into the AI, look in your own eye. Yeah? So how does it look like? Huh? Okay. So then see you in 1 hour or?
Yeah, 1.5 hours, sir.
1.5 hours. Okay.
Yeah. So
11.
we
It's
can,
11.
yes, sir.
Yeah.
We
Okay.
can wind up this session here, and
Yeah.
thank you so much, sir, for